So hi everyone. So for the second lecture tonight, what I'm going to do is just briefly cover this idea called nearest neighbor methods, which they're kind of an unusual one, but actually quite powerful. And what people often find is that if they use this method, that they can sometimes get state of the art results on almost any data set by doing so, but it's not necessarily an efficient method, and we're going to talk about some of the problems there. Okay, so there's a family of methods that can be either supervised or unsupervised, but we'll discuss the supervised versions here as kind of a continuation of what we were doing in previous methods. We will go on to some unsupervised methods, but this module is mainly going to concentrate on supervised methods. Unlike previous methods we've looked at, where we infer the model from the data, here we use the data directly. Now, I mentioned to you previously that normally what we do is we start by taking some data. We learn a model from that, so a model that kind of models the underlying process of that data so that we can then make a further prediction about data that we don't have. And I said to you that normally we start with an idea in our head about what that model would be so that we can then have an idea of whether the statistics that we gathered look like what we were expecting or not. But the point is that once our learning is done, we can discard that data. We don't need to remember it or anything like that. Our model has encapsulated the important statistics about that data for us then to use. That's the case in most cases, but it's not the case with nearest neighbours. So when we get new data, we just, in this particular case, what we do is we look at the nearest neighbours, which I'll define what we mean by that in a moment, and we make a decision based on the labels of those neighbouring pieces of data. Okay, which means that when we're making new predictions, we still need to have access to all of the data from our data set. And of course, if a data set becomes very large, that means we have to have a lot of information stored. So you can see how in a situation like autonomous vehicles or, any system that would be requiring an embedded system, this is not really going to be a great method. So let's say, for example, that you read a road sign, and you then, for that road sign, you're trying to figure out, well, what road sign is that? What I'm going to do is I'm going to look at lots of other samples in my data set and see, well, which ones is it most like? So that I can then say, I think that's a speed limit sign and I think this is the speed that it's going at. That's the idea here, but it would mean that you would have to have all that data set available to you. So the most common that we talk about is where we talk about k nearest neighbours, where k is a hyperparameter, where we basically say, let's say that k is 3, we're going to look at the 3 closest neighbours to us, and we're then going to in some way encapsulate the results from those to determine what label our new sample is from. 3 would be generally a pretty small number. You might be dealing with much larger numbers than that in many cases, but it depends on the system that you're doing. So as usual, this decision is far from simple. Okay, so deciding just what value k should be, that really depends on your application, and there's no obvious way of doing it. There are unsupervised methods for determining the value of k, such as radius-based learning, where it basically takes circles of data around our points and sees how many it should include in that, and that can work quite well, particularly where our data is structured and so on. But in many cases, you just have to decide a value for k yourself. So what constitutes a neighbour? In small numbers of dimensions, so when you're dealing with this, you're not dealing with thousands of dimensions. In small numbers of dimensions, it may be as simple as saying that the closest in terms of Euclidean distance, the closer the neighbour would be. Okay, so we have samples and we look at how far they are away from each other in terms of Euclidean distance, and then we take k of them, however many we've decided k is, and we make a decision based on that. We might have to set up rules for multiple neighbours at equal distance. That's the sort of thing you would generally have to do. But what about if you were looking at something like images? How do you decide what the nearest neighbour of 2 images is? What's your criteria for that? That's very, very difficult to do. So if we have thousands of images of like road signs, as I said, or zebra crossings, and thousands without, now you come along with a new image and you have to determine the k closest neighbour images to compare it to, as to whether it has a zebra crossing or not. It's certainly not an easy thing to do. So here's just a simple 2-dimensional example like we showed previously. And let's say I have a new sample come along. This is it here. I'm just going to show it as, well, I should maybe show it as a diamond shape or something different to what we've seen previously. So we have a new one here. And we start saying, well, okay, what are the nearest neighbours? Now, clearly, these ones are not neighbours of it, okay? We've got lots in between before we get to that. So let's say we set k to be a value of 5, okay? So what are the 5 closest neighbours to me? Well, I would imagine that that's the closest neighbour, that, and then where do we go from there? Is that one closer than this one, for example? I'm not entirely certain. We'd have to be able to measure it in some way. So now if we look at those, what would you say, what would you label this new sample as? Would you label it as an X or as a circle, do you think? What would you go for here? Okay, so Livy's going for X. Anyone agreeing or disagreeing? Jerry's going for X as well. Okay. And I think that's reasonable. But this would assume a majority vote, because it might be fair to say, I mean, it's not absolutely definite in this case, but let's say, for example, that if we just moved this, and see, does my moving work tonight? It does. Okay. Now you see this situation here where it's very, very close to that circle. It's not as close to the X's, but by majority vote, if we took k equal to 5, we'd certainly the X's would win it. But if we were dealing with some other mechanism, we might find that actually the fact that it's very, very close to this circle value might suggest to us that we should put it as a circle. So you can see that these things are not absolutely clear as to what we should do. Now, there are some inefficiencies related to this. So the other issue we have to have is that our method must in effect keep in memory all of the data samples. So in this case, that may not be a big issue to keep all the data samples, but we then got to calculate all the distances to them. But if we're dealing with thousands of images or something like that, then that's clearly going to be a problem for us. So in other methods, once we defined the model, that was that. We just got rid of the data. We didn't need it anymore. It didn't take up any space, and we did not need to remember all of the data. Now we have to search through all the data to find neighbours each time we want to classify a new data sample. And we gave the example in the last class, the last lecture that I did, where let's say you've got missing values for certain features. So you want to find the other ones that are closest in terms of the other features, and then try and fill in that gap in the data with one of its nearest neighbours, or whatever, voting of its nearest neighbours, or linear regression of its nearest neighbours. So despite all of that, nearest neighbours has been successful in many classification and regression problems, with examples being like handwritten digits and satellite images. Comparing satellite images has been very good for these sort of things. So you're trying to find the nearest neighbour of a satellite image that you haven't seen before, or a handwritten digit. Which of the other ones is it closest to? It was quite useful in that. Now, we have other better methods probably now in terms of convolutional neural networks, but nonetheless, in terms of quite a simple mechanism, this is relatively simple. It might take up a lot of data, but it's a relatively simple method, and it can often achieve very, very good results. Nearest neighbour methods are also the basis of many other more complex methods in machine learning, so they're important to know from that point of view. So we would often use a certain number of nearest neighbours, or a neighbourhood of data samples, in order to do some of the other more complex things that we do in machine learning. So it's good to kind of know what these things are. So what are some of the ways that we can decide, the question that I asked you there, and where most of you said X as being the answer, what are some of the mechanisms that we could use in order to decide how we're going to classify once we've done that? So we could use majority vote, and I think that's what you did in the previous case. Take the nearest neighbours, count up the votes for each label, most votes wins, job done. Note that in the basic algorithm, no weighting of votes due to distance. Now, if we went back here and said, well, what I'm going to do is I'm going to inversely weight it, that the further it is away, the less its vote is worth. Okay, so for example, this one now is a lot further away, so it gets a lower vote, whereas I'm going to weight this one the highest because it's the closest one. Okay, so you could make it more complex and do that sort of thing as well. So you can take the so weighting due to distance can be added to many implementations. So you can take the k nearest neighbours most common and particularly useful when the data is uniformly distributed. Or what you can do is take a fixed radius and take all the neighbours within that radius, and this is more useful in non-uniform spaces. So for example, what you could do is, so I'll just delete some of this data here. So we could decide that what we're going to do is we're going to take a certain radius around this. And I'll just move this to be centered on it, about there. And you can see there that now we've picked that one, that one, that one, and that one. So rather than picking a certain number of them, we've just picked those. And what you can then do is you can then say, let's say I've another example here. And we're going to say, well, what is that one going to be? And you can then take your circle, move it down onto that. And you can see then in this particular case, you know, have we taken one or have we taken three? Well, it really depends on whether this this one here is outside it or not. But you can see that we're taking a smaller number of them into account simply because they're further away from what was doing. So that's another way we have of doing it. And it can work well, you know, when things are not particularly uniform. As would always, if you see text in blue there, you know that you can click on it. So you can go through and find an example on Scikit-learn of a classification using this nearest neighbour method. So you can go and have a look at that in your own time. You can also use nearest neighbours for regression. So rather than voting, here we use the mean of the values of the labels of the nearest neighbours. So let's say, for example, they're not necessarily labels of they're this class or that class, they're a particular value. And what we do is we take a certain set of neighbours, take their values, and then take an average or a mean of those. Okay, so again, you can use the k-nearest neighbours or you can use a radius in these cases. That's a matter for you to decide. And as before, you can weight them depending on how far they are away, or you can just take their values on face value. It really depends on what you want to do and what methodology you come up with for it. And this is where a lot of research comes in as towards trying to figure out, well, what are the best methods that we could use. One of the other problems with this is that how do we go and check all of the neighbours and where they fit in and what the effect of them is. So there are different search algorithms for doing this, and some are more efficient than others. So because we have to search through the data so often, good search algorithms make a major contribution to this. So examples of search algorithms, and Scikit-learn make use of these, are you can use brute force, which is I'm going to check every bit of data. Okay, so if we go back to our example here, this would be, I have a new piece of data here. I have a new piece of data, and I'm going to check absolutely every sample. I'm going to include all of those and then say, actually, they're not the nearest neighbours. So I'm going to take k nearest neighbours, but I've checked every sample just to be sure. Or I've done I have a radius and I've checked every sample, and if they're not inside that radius, I don't include them. Now you can see here that this would be very grossly inefficient to check all of these when they're not within that radius, but that's nonetheless what the brute force method does. In other words, I have to check it to find out if it's within the radius or not. There's also called a KD tree, and there's called a ball tree. So we're going to look at all of these just in turn, and then we'll finish up on that. So the brute force method, this means computing the distance from a new sample against every sample in the data. This word, or the word sometimes used for this type of algorithm, is called naive. So if you hear this word naive, it basically means that we're not really being clever about this at all. We're just going with the simplest method, which is often inefficient. We can look at how expensive of an operation this is by considering how the algorithm scales with the number of samples and the number of dimensions that we have. So the number of dimensions here is given by D, and the number of samples is given by capital N. And you can see here that as the number of dimensions goes up, the order of the problem scales linearly with that. Now that doesn't tell you how long it's going to take to compute on a particular piece of hardware. It simply says if this takes 30 seconds to give you a result on a particular piece of hardware, if I double the number of dimensions, then it's going to double the amount of time it's going to take to find to do this brute force version of it. If we double the number of samples that we have to check, then we actually get 4 times the amount of processing it's going to take in order to do that. So this is the kind of order of operations that is going to take. So this means that it scales linearly with the number of dimensions and quadratically with the number of data samples. How efficient your hardware is will tell you the rest. This simply tells you how it scales, no matter what the hardware would be. So we mentioned this KD tree, so k-dimensional tree. This recursively partitions the space along the data axis, dividing in two each time, which is like a binary search tree. So you're talking about straight lines here that you're dividing up the space into. It divides the space into orthotropic regions, in other words, that would have the same sort of size. And this is more efficient by attempting to remove redundancy. So the idea is that, the basic idea is that if we know sample A is very distant from sample B, and we know that sample C is close to sample A, then we can be fairly sure that C is very distant from B without actually doing that calculation, and therefore not including it from that point of view. So by having the space divided up in this way, we can be a little bit more sure that there are certain parts of it that we don't need to check. Okay, and this can make things a little bit more efficient. So we can only ignore that data then in that case. The cost of the computation for this algorithm is as follows. So by dividing that space up into two each time, we actually have log to the, you can see that we have a kind of a log function related to this. And basically what this means is that we now say that if we double the dimensions, then we double the time. But if we go up in terms of, if we double the number of samples, then we don't actually, we don't double it. It's more than double, but it's less than quadrupling it. So it's less than the squaring of it. So you can see here that as n goes up, log n also goes up, but goes up by a smaller amount as we go. So therefore, this is a good deal better than the squared term that we had last time. So there is also a one-time cost for construction of the tree as well. You're going to see these trees pop up in what we'll call decision trees and random forests in a later lecture as well. So we'll see a little bit more about them at that stage. The other one then is called a ball tree, and KD trees are still inefficient if the dimensionality is high because it's harder to divide up the space in that way. Ball trees partition the data as a series of nesting hyperspheres. Now, hyperspheres sounds like this very complex thing, but all we're basically saying is if you think about a sphere in 2 dimensions is just a circle, right? So a sphere in 2 dimensions is just a circle. A sphere in 3 dimensions is a sphere. What's a sphere in 4 dimensions? It's called a hypersphere. So once we go above 3 dimensions, we call these things hyperspheres, but we're eventually just having a radius that goes out in every one of our axes by the same amount. And what we're then saying was we kind of partition the data within those regions. So ball trees partition the data as a series of nesting hyperspheres. The one-time cost of tree construction is much higher, but it can be very efficient on data that is highly structured. Performance here is not strictly defined as it is dependent on how structured the data actually is. So it's difficult for us to tell the order of it and how it will scale because it depends on how structured the data is. And basically, a single measurement can be made to the center of the hypersphere, and then there is an upper and a lower bound on the distance to all samples in the hypersphere. So this is handy. We basically group all things together within one of these spheres, and what we can then do is just use the value of the center of the sphere for our calculations, and we say if it's within that range, if it's within that sphere, we take the same value in each case. If the data is not well structured, you'll end up with more of these spheres than you really want, and therefore it's diminishing returns, and you end up having a lot more distance measurements. Okay. So that's nearest neighbours. I'm going to finish there on that. Acknowledgments there to Scikit-learn. But I don't know if I went on to the last slide in the last lecture, but mainly, as I said, that was taken from Stephen Skeena's book. Okay, so we'll leave it there for tonight, guys, and I will chat to you later in the week. If you have any questions, obviously put them up on the forum as well, and I'll try and answer them there.